There it is. Second time's the charm. All right. Any questions on the warm-up? Yeah? No? Okay, good. So 2.3, we're learning differentiation rules. So, first of all, what is differentiation? It's a buzzword in education. Yeah. 2.2? Oh, this, okay, it's an S, and then it's a spooning S below it. Okay, it's two spooning S's. This is the typographical symbol for section. Okay, it's the typographical symbol for section. It's two spooning S's. Yeah, it's a pretty cool symbol. Section 2.3. Yep. All right, cool. Any other questions? Differentiation in education means making a different task for each and every one of you in this class, depending on your individual abilities, which is really hard to do, right? So we'll talk about differentiation from a calculus perspective instead, okay? Differentiation is basically the process of taking a derivative, or you could say finding, whatever you want to call it, finding a derivative. And the derivative, of course, then could be a function of x into which we can plug values to find slope, set it equal to a value that we want the slope to be, and solve for x. Or it could be finding numeric slope, right, with the modified form and the alternate form. So differentiation is the process of finding or taking a derivative. We're going to learn some rules now that will allow you to find that derivative function without using the limit. Yay! So AKA shortcut rules. AKA shortcut rules. And some of y'all know the power rule already because we've kind of alluded to it. So before we start, I want to emphasize these two things, vocabulary essentially. dy dx is, remember, the Leibniz notation for the derivative. It is a noun. dy dx is a noun. Remember, it is similar or analogous to delta y over delta x. Delta y over delta x is a slope of a secant line. It's the average rate of change. It's measurable changes in y and x. dy dx is slope at a single point. It's the instantaneous rate of change. And it's the infinitesimally small immeasurable change in y and x. But dy dx is a noun. It's essentially equal to y prime. Okay? It's the same thing. Whereas d dx is a verb. Okay? If you see d dx, it's like kicking the y out of the numerator. It tells you to take the derivative of what follows with respect to x. So you usually have something in there. It'll look like that. It'll say d dx of. And so the instructions may just say to evaluate. That means you're going to be finding the derivative of what follows with respect to x. Now you could write it in the numerator. It could look like this, but that gets a little bit kind of tedious to write. So we usually kick it out of the numerator and write it like that. So d dx is a verb. Dy dx is y prime. It's a noun. All right, so here's the constant rule. Ready for it? First rule of the day. The derivative of a constant function is what? 0. It's nothing. The derivative of a constant is 0. That is, if c is a real number, then here's the verb format. The derivative with respect to x of c. That's what we call it. The derivative with respect to x of c, or the derivative of c with respect to x, either way, is 0. There's the verb form. The derivative of a constant is 0. Here's another way to do it in the noun form. If y equals c, then dy dx is 0. All right. So that makes sense. If we think about it from a Leibnizian perspective, a constant graphs as a horizontal line, yes? And if the derivative from a Leibnizian perspective is the slope of the line at any single point, what's the slope of a horizontal line at each and every point? 0. So there you go. The slope of a line that's horizontal is 0. If you look at it from a Newtonian perspective, it's the instantaneous rate of change. Well, if the y value is a constant, how fast is the y value changing if it's a constant at any point? It is not, right? By definition, it's not changing. It's a constant. So that would be the Newtonian perspective. So there you go. What's the derivative of a number? 0. Yeah, let's try out our first rule, shall we? All right, we need some practice with this one. Notice we don't have to set this up with the limit definition. Find the derivative of the following functions. All right, so we're going to practice notation as well. Here's essentially what we're doing, and I'm not going to write this every time. but we're taking the derivative with respect to x of both sides. And it's not commutative, so the d dx goes in front. It's kind of like multiplying both sides by 5. We're taking the derivative of both sides with respect to x. The left side becomes dy dx, basically because we're sliding the y into the numerator. And we get the noun. And what would be the derivative of 8? 0, right? How fast is 8 changing? It's not. Now, you could go straight from here to here. When your function is solved explicitly for y in terms of x, like we have it up there, y equals, you could just go straight to dy dx equals 0, okay? But this is the middle step with the asterisk is what we're really doing. Okay, super. Or, here's another one. You could also use y prime. They both mean the exact same thing. Y prime is a little bit faster, but of course y prime, if you're not paying attention, sure looks a lot like what? Y prime looks a lot like y to the first. Are they the same? No. The left one is y prime. The one on the right is y to the first. What's y to the first? It's just y. So I kind of stay away from y prime because it's real easy for you to, as you move further through the problem, say, oh, that's just y to the first. I don't even need an exponent. Silly me. And you start calling it y. But dy dx stands out pretty prominently, yeah? You're not going to mistake dy dx for y. And it's also a constant tribute to Leibniz. All right. Let's do letter B. F of x is equal to 0. So if you have function notation, again, you're taking the derivative of both sides with respect to x. But if it's solved explicitly for y or f of x, you don't need to show this step. I'll show it one more time. It would be the derivative with respect to x of f of x and the derivative with respect to x of 0. That's essentially what we're doing. This becomes f prime of x. So when it is in function notation, we call it f prime of x. That's going to be less likely to just say, oh, that's f to the first, because there's an of x behind it. So we typically do that. And then the derivative of 0 is what? 0. Ooh, it's its own derivative. Sweet. It's nothing, and it doesn't change. Wow. And it lives in its parents' basement, right? 0 is absolutely nothing, and he's never changing, right? At an instant or average between 2 points in his life, he's never changed. 0. Okay, good. Letter C, you do. Practice your notation. That's really what we're doing. The answer is 0 to all of these. We're just practicing our notation. Yep, good. Yep. Equals, right? There we go. If you want to show that d whatever in the intermediate step, that's perfectly fine. Okay, here's what it would look like. d dt now, right? Not the banned pesticide, ddt, but the derivative with respect to t of both sides. So that would be the step that you could show if you like, or you can omit if you like. The derivative of s is going to be s prime of t, and the derivative of 3 is 0. So if it starts in function notation, the independent variable goes in the denominator, whether it's a t or an x. It stays in function notation. But you could also do this. You could also say that that's the derivative of s with respect to t. Okay, so the dependent variable is in the numerator in Leibniz notation, the y essentially, and then the denominator has your independent variable. You're looking how fast things change with respect to that variable, which in this case it could be time and s could be position. So its derivative would give us the instantaneous rate of change of position, which we call what? Velocity. Yeah, cool. All right, letter D. Go ahead and take the derivative of y equals k pi squared, where k is some constant. K is a constant. Yep, good. Yeah, good. The quickest, fastest way to do it is just say y prime equals, and pi squared is a constant, isn't it? It's like 3.14 squared times another constant k is another constant, so its derivative is 0. So that would be the shortest way to write the answer. Or, of course, if you want to shout out to Leibniz, you could say dy, what's the variable here? usually x, right? If it's a constant and you're not sure what the variable is, you can use x and be safe, like if it's dy. We typically use y's and x's. Okay, so that's fine. And Leibniz notation is a little bit better in that sense because it does also define the independent variable, which for a constant you're not going to see. So it's kind of like function notation. All right, yeah, there it is. So any questions on the constant rule? No? Okay, good. Here's the power rule, or as I sometimes just refer to it, it's the powerful rule. It's probably the single most used and important and cherished shortcut differentiation rule that's out there. Now, this rule that we're about to learn didn't just fall out of the sky or just get imported from France or something. This rule that we're about to learn actually is a distilled result of the limit definition of the derivative. Okay? It's a distilled version of the limit definition of the derivative. So it was generated that way. Here's what it says, though. If n is a real number, any real number, and a is also some real number in the function a times x to the n. All right? So we have something written as independent variable x raised to some power, could be any power, times some constant a. Right? Then the derivative of ax to the n with respect to x, that would be the verb format, is an x to the n minus first. Okay? Real easy to generate that. All you have to do is multiply first. You're multiplying the exponent times the coefficient to get your new coefficient. And then once you do that, you've used the exponent. So number 2, you subtract 1 from it. You deplete it by a single value. All right, so the derivative of a cubic is going to be a quadratic. The derivative of a quadratic is linear. Every time you take the derivative, it comes down a single full degree. All right, and you could prove that in your spare time if you'd like by doing the limit definition. Okay, it's really hard to do binomial expansion though for a general power n. So there are some theoretical things in there that we probably haven't had. Okay, but there's proofs online if you're interested. All right, so here would be the noun format. Equivalently, if f is equal to x to the n, or f of x, then f prime of x is, ax to the n, then it's an x to the n minus 1. So we're basically multiplying and subtracting in that order. Multiply, then subtract. Multiply, then subtract. We could do that, right? Multiply and then subtract. Multiply, then subtract. Let's try it out. Find the derivative of the following functions. Here we go. F of x is 2x cubed. Well, that's written in the form a times x to the n. So f prime of x, you don't have to show the d dx of both sides. It's solved explicitly for y or f. Equals, let's see, 2 times 3 is 6, so there's your new coefficient, times x to the 3 minus 1 is 2. We're done. It's 6x squared. How joyful is that? Not very, I agree, because it does rob you of some of the joy. How can we check that? Well, we could also say f prime of x is the limit, as h goes to 0, of 2 times x plus h quantity cubed minus 2x cubed all over h, right? And when we plug in, we'll get 0 over 0, and to this one we would apply the what? We would apply the sledgehammer to it, right? Boom, boom, and expand it out. This is not very fun. You'd have to foil that and then foil it again. This would be kind of like a 5-pound sledge, right? You can't just call it x cubed plus h cubed. So you can imagine if that were like x plus h to the 5th power. Ooh, it's really, really hard. Not hard, but labor intensive, I should say. Tedious work to expand a polynomial that's larger than degree 2. If it's degree 2, it's just square multiply double square. So the power rule came from that and for general power n, but now the distilled product is just, hey, just multiply and subtract. So we're actually finding the answer to this over here by multiplying and subtracting really before we even set it up using the limit definition. So I don't know who gets credit for the distilled product, but it has evolved to the point where we can just use the power rule. Now, I did have a student who went to UT a long time ago, and in his Cal 1 class, he was in engineering at UT. His professor made them set it up using the difference quotient each and every time. Did not allow them to use the power rule, okay? And he called it the Newtonian Quotient. I'd never heard it called the Newtonian Quotient. But Jeff Kowalczyk, if you're listening, Jeff, had this professor, and I saw him at the tailgate party, and I told him, dude, drop that course. And I think he did and got into a different class because, I mean, I could see knowing how to use it, but for every problem, that's like saying, hey, man, we have a car. I'll let you sit in it, but you're going to have to walk everywhere you go, right? You've got to leave your car parked in the driveway, right? Oh, man. We've got to use the technology, quote, unquote, that we have. But we always appreciate, the horse and buggy and whatever else came before that. Letter B. G of x equals the cube root of x thirds. Ooh, if we set this up using the limit definition, we're going to have to do some serious ratcon with a cube root instead of a square root. I wonder if there's a better way. Well, yeah, there is. If I can write g of x in the form a times x to the n, where a and n are any real numbers, it could be any real numbers, fractions, negative, whole numbers, whatever, then I could use the power rule, but it has to be in that form. So sometimes there's a little bit of rewriting on the front end before we can jump in and use the derivative. So working straight down, I'm still calling it g. What would that be in the form ax to the n? Good. 1/3 is the coefficient times x to the 1/3 power. There you go. That is now in the ax to the n format. So now on the next line, we're going from g to g prime. You need to make sure you show that. That's one of those notational things that you need to show. G is that, and now g prime is, well, we multiply and subtract, right? 1/3 times 1/3 is 1/9 times x to the 1/3 minus 1 is, and this is where we get really good with fractions in our head, negative 2/3. Good. There's the derivative. Okay, so what we're going to do now is, since it started in such a nice form, this was just an intermediate format for us, we're going to put it back into the other form, which if we're using this, we do want to put it back in the other form. So hopefully you can do it in one step. That's 1/9, and then x to the negative 2/3 gets put back as the cube root of x squared. There you go. Okay. Now notice, is x equals 0 in the domain of g? Is x equals 0 in the domain of g? Yeah. What do you get when you plug it in? G of 0 is, cube root of 0 is 0, 0 divided by 3 is 0, you get 0. But is it in the domain of g prime? No, you get 1/0, which is infinity, right? Okay, so is this function differentiable at 0? No. So you can actually determine if a function is differentiable, if the derivative exists, just by analyzing the domain of the derivative. It's continuous at 0, but it's not differentiable at 0. This is one of your parent functions, right? Remember the parent function, a cube root of x? This is just 1/3 times the cube root of x. So it takes that function that, remember, had a what at 0? Vertical tangent. And all it does is it vertically compresses it by a factor of 3. That's it. So this is the sneaky one, right? So notice that the derivative knows that the derivative is not supposed to exist. In fact, when you plug it in, you get positive infinity. Okay, when you take the limit on both sides, it's a positive number. So pretty cool. The functions are communicating somehow through this mathematical ether. It works out. Pretty neat. All right, letter C, do it yourself. Some of y'all are already done. Watch your notation. Practice it from day one. Don't let yourself slip and do it real sloppy like, because then you're just reinforcing bad habits. Don't smoke or vape or juul or do meth or crack or anything like that either. Okay, it's all gateway stuff to bad things. That's not a x to the n. That's a 1/x to the n. So you got to bring that to the top. Yeah. You have to be able to write it in that format. Some number times x in the numerator to some power. So if you're stuck already, here's the rewriting. That would be 5/3 as a coefficient times off to the side. We'll put the x kind of on the same level as this bar. When you bring pi to the top, it becomes negative pi-th power. Wow. Have you seen anything to the negative pi-th power before? No, not really. Okay. But it works. The power rule works not just on nice integers. It can work on irrational numbers as well. So there it is in the form a times x to the n. So if you take the derivative of both sides, you get y prime or dy dx. I'll tend to use dy dx, but I'll use both for now. Y prime equals, multiply, and you get negative 5 pi thirds times x to the negative pi minus 1th power. So what a fantastically exciting exponent, negative pi minus 1. So that is technically the derivative. But if we wanted to use this, we would want to put it back in the original format. So that now becomes negative 5 pi all over 3x to the, what would the exponent become in the denominator? Is it just positive pi minus 1? Pi plus 1. Good. You have to change the sign of the exponent, which means if it's two terms, you multiply it all the way through. Or off to the side here, let's do this. X to the negative pi minus 1 is x to the negative pi plus 1. So when you change the sign of the denominator, it really changes both of them if they're more than one term. But pi minus 1 would be a great answer choice on the test, wouldn't it? Yeah, it would be. So notice I'm done right here. I brought my equal sign straight down. If it's the last line, it's kind of nice to bring the dy dx down with it so that you kind of have the function there. All right, let's do this one very quickly together. Y equals 6x to the negative 3/5 power. You could bring that all to the top in one step, hopefully, negative 3/5 power. And now it's in the form that we need. So dy dx, the derivative of both sides, gives us dy dx on the left. Negative 18/5, that's negative 3/5 times 6, times x to the negative 3/5 minus 1. That's negative 8/5. Because 1 is equal to 5/5. So we're getting real good with fractions, like I said. And there's your derivative. And then if we clean it up, that's negative 18 all over 5 times the 5th root of x to the 8th power. That final cleaned up version is a lot nicer to use later on. Right now we're just practicing how to find them. We're going to be using these things for other things later in this chapter. So have a fantastic lunch.